So Pascal, the floor is yours.
Thank you very much, and good morning also from me. It's my pleasure to be here today, so thanks for the organizers to put together this very nice program this week. I hope you all had a fun afternoon yesterday and also evening, so I'm very happy that many of you are here in the morning in this early session. I have the whole morning, and I split it in two parts. So I will first cover some theory and then later have a hands-on tutorial, and we'll just have to break in between. And depending on the timing, we might shift the break a tiny bit. And I would like to encourage all of you to ask questions all the time in between. So just raise your hand or just ask directly if I don't see it. But please interrupt me. The first part will be a bit theoretical, a bit mathematical also. And if there's anything that you don't fully understand, just raise your hand and I'll try to explain it again or rephrase it in other words. And if you have any questions, please ask in between. So don't hesitate to interrupt me. Yes, please. Yeah, I will get to that in a sec. Okay, so let's start. Yes, imagine you have some experiment. And when I say experiment in this lecture, I mean it can be a lab experiment, like physically you being in a lab, or it can also be a computational experiment. You're running a simulation, you're running a machine learning model training run or something like that. So experiment can be anything. And imagine you have a knob like that you can turn. Can also be a computational knob where you have like some hyperparameters to change or something like that. And you have an observation. You have a number that you see that comes out after some time, after you run the experiment, and your goal is to maximize this number. The problem is you don't know the relationship between how you set this knob. So what is the knob setting and how is this number? It can be linear, that would be easy, but it can also be non-linear. So there might be some optimal knob setting that maximizes this number. There might be also some multiple optimal knob settings or like a semi-optimal one. And your goal is to find how should I put that knob in order to maximize that number. So now it's already on you. How can someone come up with a strategy of how would you find the maximum number here by optimizing the knob setting? All the points, yes. That would be the very... Yes, and if you then see that it's very slowly only varying, what would you do then? Yes.
If I'm really far away, and then I will try to go by the extremes and try to make it shorter.
Mm-hmm. So you can easily come up with strategies. Does anyone have an alternative idea? Yeah.
Try some different positions and turn it just a bit to see the derivative.
Mm-hmm.
And get different points.
Yes. That's also a good strategy. You can like try changing it a tiny bit to know in which direction to go, and then you can jump maybe a bit. So there's many options of doing that. But now let's go to another lab, and suddenly we have two knobs. So what would be a good strategy here now? Yes, so that would be the extension of trying all the settings. You kind of try all the combinations of settings. This would be one approach, but then we can always like go a bit further. Can also go to a realistic lab where we don't have 2 or 3 knobs, but many of them. This is again true also for experiments on the computer. We have like, if we train a neural network, we have the number of layers, we have the learning rate, we have the size of the layers, we have all kind of things we need to decide. In a real world lab, I don't know, where we want to synthesize a new material, we have some, I don't know, if we think about nanoparticle synthesis using lasers, we have a couple of laser settings, we have the initial conditions, temperature, environment conditions, we have solvents, additives, we have a lot of choices to make. And there's probably only one optimal choice, or maybe a range of optimal choices that maximizes this number. And I think we kind of agree that trying all combinations in this setting here would be quite tedious. So even if we just say we have, I don't know, 7 settings here per knob, that would already be 7 to the power of 8 possible combinations. And I think none of us, even if we have a super high throughput experimental lab or the biggest supercomputer, we don't want to run 7 to the power of 8 experiments here all in parallel or sequentially. So this is really tedious. And that's why I will talk today about how can we use machine learning methods, particularly Bayesian optimization, which is a combination of an optimization algorithm and a machine learning method to solve these type of scenarios in a data efficient way. So the goal today is data efficiency. We want to optimize or get optimal results with the least amount of experiments possible. So the trade-off here is not just by brute force getting the best results, but really try to get them with as few experiments as you can possibly do. So we're exploring kind of the Pareto front of being cost efficient, like having few experiments and getting very good results. And this is used in many different areas. So I hope that this is an algorithm that I'm presenting today that will be useful to many of you. It is the main algorithm that's used in self-driving labs, and we will hear some of it in this talk and then more in the talk of Özlem in the afternoon. But it can also be used, and it was, I think, originally been used to hyperparameter optimize machine learning models, because there we also have this problem of having too many choices and only finite compute time, so we want to find optimal hyperparameter settings for machine learning models. And everyone in this room who is doing ML potentials, you might have the similar problem, even though very often we ignore it, we just take the default parameters. But if you train your ML potential on a very specific data set that you generated, and that has a very specific size, number of data points, then the default settings might not be optimal. You might want to go to deeper or less deep neural networks, slightly different parameters depending on your problem. If we talk about models like Nequib or Allegro that have these spherical harmonics, you want to maybe go to different parameters in the spherical harmonics. So there's a lot of choices that are maybe hidden to you, but there's a lot of choices that are already done for you, and you might want to optimize those as well. So I hope this is an algorithm that's useful for everyone. But before I start into it, I would like to do a quick test. Who already did use in the past Bayesian optimization in some sense? So roughly 7, 8 people. Who of you already implemented it yourself? Like you really did all the steps? Okay, more or less everyone who is using it also implemented it. Who of those who didn't use it yet, who already heard of the algorithm? Okay, so most of you already heard of it. Okay, so for those who didn't hear it at all, this will be all new. For those who already used it, maybe there's some mathematical part that is new to you. So I hope everyone benefits a bit of the lecture today. So before I start, I would like to quickly introduce my group at KIT. So we work on all kind of method development aspects of AI and machine learning methods for materials design. So apart from the things I will tell you about today, we also work a lot on property prediction, inverse design. One focus area is explainable AI. So if you have data sets where you want to learn the structural property relations more than just doing accurate predictions, please also feel free to reach out to me. That would be a nice collaboration project. We work a bit, not so much on the ML potentials. We're not a developing team for ML potentials, so we're, as most of the people in this room, more on the application side. We specifically focus here on active learning and reactive systems, also excited state systems that are a bit more tricky to do with the, let's say, out-of-the-box methods. We recently started looking into foundation models, LLMs mostly for data extraction of some data sets, and I think there's some of you in the room who do similar approaches. And then we became part of a Helmholtz foundation model initiative that tries to develop a foundation model for materials. So we try to combine many different data characteristics or like measurement characteristics of materials in one joint foundation model in order to use it for many different downstream applications. And today I will mostly focus on this aspect of my group, which is the self-driving labs and the algorithms for that, so to automate basically decision-making processes in automated labs and also in experiments, in computational experiments. And the idea of self-driving labs is that we have a very interesting experiment, and as I said, this could also be a simulation or some computational thing, and to some extent we automate this, which is a bit more tricky or much more tricky in actual physical experiments than in computation. So if you do computation, I encourage you anyway to always do the full automation, because that makes everything easier and you don't waste a lot of time setting up things again and again. So everyone who is doing ML potentials and all that stuff, please automate everything that you can. It will make your life so much easier. Don't run simulations manually. If you think you will run them a second time, please always write some script to automate everything. And then the idea is that we can, of course, like run this many times and look at the data and see what is working good, what hyperparameters are working better, what synthesis conditions are working better. But we can also use the data in this closed loop way to learn from every new data point. So it's the extreme case of active learning. We're not like generating a large data set and then training our model, but we basically, every time we have a new data point, we retrain our model and then use that trained model in order to predict what is the best next experiment, best next simulation to do. And then our machine learning brain here tells us what is this optimal set of knobs that we should try next in order to be as data efficient as possible, in order to create the most informative next data point to run here in an automated way and feed this back into the machine learning model to learn from this new data point. The automation part here, by the way, is also to some extent optional. I mean, I just encourage you to automate everything you can, if you can, but sometimes the overhead of automating is also too large. So you can, in principle, also just couple some manual experiment, some manual simulation with Bayesian optimization in order to get the most data efficient way of exploring your parameter space, your knob setting space. So you don't necessarily need to automate every single step, especially in experimental context. That's not always needed. You don't need to spend, 2-3 years in automating every single aspect of your lab. Very often it's sufficient to optimize some key steps, or to automate some key steps, maybe not even anything, and you can still benefit from algorithms like Bayesian optimization to make clever choices of what experiments to do, especially if you have many different parameters that you want to optimize simultaneously. So how does this work? We have here experiment simulations, some automation, typically robotics or just scripting of simulations. And then we need some machine learning models here that do the decision-making process. And my group is working on various aspects of this group, of this third part here. Sometimes the data that is coming from the experiment is very complex. It's not just a number, but a spectrum or something like that. And we would need some automated data analysis in order to make sense of that number in an automated way rather than analyzing every single spectrum, every single diffractogram, and so on. So we need sometimes machine learning for data analysis. Then we need the decision making, and this is what I will talk about today. And then sometimes if this involves making new material, making new molecule, and the algorithm suggested, please make this particular molecule that's most informative, most promising, then of course we also need to predict the synthesis conditions or optimal synthesis conditions. So very often we have like a small side optimization loop here that helps us then decide not only what material to make next, but also how to make that material in a very efficient way. So this can be a bit more complicated than just the Bayesian optimization itself, but today I will focus on the decision making based on Bayesian optimization. Just one example before we start with the theory. This was a project that we did in the last 2 years with the Helmholtz Institute in Erlangen-Nürnberg, and the objective here was designing an optimal catalyst. So the catalyst consisted of a composition of different metals, and we had 2 objectives. We wanted to have a catalyst that maximizes the activity, but at the same time we didn't want a very unstable catalyst, and very often these 2 things don't agree very well together. So the most active catalyst is the one that dissolves very quickly, and the one that's super solid and doesn't dissolve at all is not very active. So we have a Pareto optimization here. We want to have objective 1, maximizing activity, and at the same time maximizing the stability, and we want to basically explore this Pareto front. So we want to see how far to the top right can we go here. And what were the knobs? The knobs was basically the catalyst composition. So we could change the amount of different metal compositions that we had in this catalyst. And we did exactly that loop. So we had a couple of initial catalysts to quick start the algorithm, and then we started a loop. So in every single iteration, we made one or a few catalysts, new compositions, measured the activity and the stability. I mean, that was not done in my lab. That was done in Erlangen. I don't have any experiments in my own lab. And then we trained the Bayesian optimization or the Gaussian process model here using that new incoming data, and then use Bayesian optimization to decide what is the next best catalyst or the next most promising, most informative catalyst composition to try out. And then we ran these experiments, got back the data, got a few more data points here in this grid, and then learned again how to expand that Pareto front to the top right in order to find better catalysts. We could show that basically This is two lines that you see here. So this is the hypervolume. That is basically the volume of this Pareto front. And the higher up we go to the further right, the higher this volume gets. So we don't really care whether we are more expanding in that direction or in that direction. As long as we are expanding the entire front here, we are happy. And then we compare two algorithms. So this on the x-axis is the number of experiments we had to do. And we compared the brute force search, randomly trying many different compositions. That's the gray line, to the multi-objective Bayesian optimization, where we tried to systematically expand this Pareto front. And you can see here that after some initial experiments, the Bayesian optimization really benefits from having more and more data, and gets very, very good very quickly, expands that volume to almost the maximum, whereas the random optimization is not as efficient because we're not benefiting from that new incoming data at all. We are more or less randomly exploring without knowing what we are actually finding. So this is, of course, less efficient. And we could show here that this can be done much more efficiently. With fewer data, we can reach much higher values in this hypervolume, and that again translates to better activity and stability. And this is, of course, not the only paper that has been done in this area. There have been papers already in 2018-19 where they tried in Vancouver mostly, also in Erlangen, the team of Christoph Brabeck, where they tried to optimize all kind of different polymer compositions for solar cells and all kind of different materials properties. I think also Helge Stein, who just left, where is he gone? He was one of the first in 2018 to explore experiments using Bayesian optimization. So let's look into how it works. So the general problem setting, and I think everyone understands this now, we have multiple parameters. So we have an optimization problem. We want to maximize or also minimize something. In simulations, very often we want to minimize some error. So it's not always just a maximization problem, but it doesn't matter mathematically what you do. So we have some optimization problem, and we have multiple parameters. I write many here, because if you have only one or two parameters, then very often it's not so much helpful to already use Bayesian optimization. It can help, but sometimes it also just helps to try some combinations. If you have something like 3, 4, 5 parameters, this is already getting very useful. If you have a lot more than 10, then it can't do magic for you. So if you have really 10 parameters or more that influence your objective function, then you will not get around running many experiments, because that's just a very, very large parameter space. If you think about, even if you just think of this parameter space as having 2 settings per parameter, so let's say we have a lower and a higher setting, then this is already 2 to the 10 possible settings. So 1,000 possible settings for if you have 10 parameters. And that's just basically exploring the extremes, exploring the corners of a hypercube. And if you want to then also explore the inside and have more than 2 settings, of course, that's a huge parameter space with millions of, or a lot of points. So it can't do magic for you. You will still need to run a lot of experiments or a lot of simulations in order to explore spaces like that. Bayesian optimization can help you, but then there's no guarantee anymore that we find the global maximum in such a large parameter space. So when I write many here, I'm talking about something between 3 and 8 or so, which are still very challenging problems. And as I said, examples are chemical synthesis, where we have concentrations, temperatures, times, or all kind of other experiments that you can think of. So very often we have parameters and some objectives. And one possible solution, as we already said, is trying out all combinations, but this kind of explodes. If we visualize this as like this hypercube, then we see that there's a lot of points very quickly if you increase the dimensionality, and it's always the number of levels per parameter that we want to do to the power of the number of parameters that we want to try out. And that is the number of experiments that you can do in a grid search. And the goal of Bayesian optimization is to reduce that number and still find the global optimum, the best point in this multidimensional grid, or at least a very good point. And one approach, and this is really dating back like decades, or a whole group of approaches, is what's called design of experiment. So people have been trying to solve this problem for many years, and coming up with algorithms that are just better than this grid search. So one very intuitive way of doing it is the one factor at a time optimization. So you can basically start from somewhere in your grid here. Let's say we pick this point, and then we fix all the parameters but one. So we just vary one parameter. That's a very easy problem. We understand what's going on. We can easily find the optimum using just 5, 10 experiments. And then we go to the best point that we find, and then fix this parameter, but now change another parameter. So we first, optimize on this line, and then we see that the optimum is down here. So we should minimize that z direction parameter. And then we optimize the second parameter here by fixing all the others, and we find this should also be minimized, so we should also use the lowest setting. And then we optimize the third parameter, and we find that this corner here in the back has the highest objective function value. Does anyone see a problem with this algorithm? Why doesn't that solve all our issues? Yes, this is almost guaranteed to find a local optimum, because you kind of always fix most of the parameters. It will find some probably local optimum, or at least the neighborhood of a local optimum, but it will not guarantee find a global optimum or something that's close to the global optimum. So if you're happy with just a very good optimum, might be helpful. This also gives you quite a lot of insight, but sometimes it might also be misleading. So once these parameters are not independent of each other, you might be misled by just assuming that once you fixed parameter 1, that for all settings of parameters 2 and 3, this would also be the optimal setting. So if you now repeated this and try to optimize again parameter 1, then you might find that you're not in the optimal setting of parameter 1. So it might be better again to go up here. So you can repeat this infinitely, and you might still not find a global optimum. But there's a lot of algorithms that are all part of this design of experiments area that try to find clever ways of getting away from this cursive dimensionality. And Bayesian optimization, some people say it's part of design of experiments, some people say it's outside of that. It defines a bit of what exactly you define as design of experiment. But from a, let's say, historical perspective, very long design of experiment was setting an initial budget, and it was then designing basically all the experiments you do a priori. So you did not learn adaptively from new incoming data, and that's the magic of Bayesian optimization. You learn from incoming data and use that and exploit that incoming data to make more clever decisions and more efficient exploration steps to find global optima. But some people also say these adaptive algorithms are part of design of experiments, so you might find misleading literature. Some people claim Bayesian optimization beats design of experiment, and then reviewer 2 will very likely say that's already part of design of experiment, so you can't beat it, and then you will fight with the reviewers. So be aware that there's multiple different definitions of that. Okay, so in the following couple of minutes, 10, 20 minutes, I will introduce the Bayesian optimization algorithm. And Bayesian optimization always needs some machine learning model that learns from the data. So Bayesian optimization itself is a optimization algorithm. It's not a machine learning model. It's an algorithm that tells you what to do in which sequence. And it needs a machine learning model that learns from the data, and very often Gaussian process models are used in Bayesian optimization. There's no rule that you have to combine Bayesian optimization with Gaussian processes. It's just the most convenient way of doing it. That's the main standard way that's implemented in most Bayesian optimization packages, but they are not married. So you can as well use Bayesian optimization with some other machine learning model. And I will tell you later what are the side conditions that you need to think about when you choose your machine learning model here. So I will introduce the algorithm. I will introduce also Gaussian processes, because that's also outside of Bayesian optimization a very useful small machine learning model that's very easy to train. Doesn't really have hyperparameters because they're optimized on the fly, so you don't need to worry too much about overfitting, things like that. And if you have small data sets, very often Gaussian process models, also just as a standalone prediction model, are very, very efficient and can be used for many problems. So whenever you use random forests, gradient boosting regression, and so on, you can as well try Gaussian processes to see whether they're maybe more data efficient than your other machine learning models. Then I will talk a bit about decision making in more complex workflows. I introduced this very simple loop where you do one experiment at a time. You immediately get out your your objective function value, and you can learn from that. But sometimes you want to have much more complex workflows where you have, I don't know, a simulation that you can run, you have an experiment you can run, you want to learn from both. So we'll talk a bit about extensions of that simple Bayesian optimization algorithm to these more complex workflows. And then later in part 2, after the break, you will all see 3 different ways of implementing this, using this practically. I will first show how we can implement Bayesian optimizations in more or less 100 lines of code without any package, only NumPy. So I will walk you through a tutorial. You can also program with me. So we can all try different optimization problems and then see what works best. But this is not how typically this is done. So you don't implement it yourself. You use some packages that are implemented for you that all have very convenient functionality. So I'll introduce the X and the blowtorch package. And this is basically code that you can already use to optimize your own experiments. And then in the third part, I will introduce some software that a startup that I'm co-founder of is developing. And we do have right now a free trial for academia. So if you want to enter our academic program, you can also use that software, and then you will also get support. So the team of Excello will then talk to you about what you want to solve, and then help you set up the Bayesian optimization, set up all the tools, and guide you through a couple of weeks or months of one experimental campaign. So I'll show you in the second session 3 different options of how you can use that in a practical way. Okay, are there any questions so far about why we're talking about Bayesian optimization today? Okay, then let's start right into it. So let's go back to our knob problem. Imagine we have here a single knob. Very easy because that we can visualize here. But everything I'm now explaining to you is also applicable to many knobs. So it's just for visualization purposes. I only chose to have one parameter that I call X. And this is basically the thing that we can change in our lab setting. I don't know, the learning rate of our machine learning model training or the temperature in our catalysis experiment. And then we have one parameter that I call F, and that's the observable function that we want to optimize. So this is the number we observe after running the experiment. And then we have one line here. That's the function f of x. So how does our observable depend on x? And here I'm plotting this. You see there's a global optimum, there's a local optimum, there's like bad points. But of course, usually we don't know this. So this black function, you see it here in my slides. But usually if you start an experiment, you don't know anything about that function. So here, for visualization purposes, I plot it. But usually you're completely blind in the beginning. You only know you can change parameter x, but you have no idea how f will react to these changes. Okay, and then we can do some initial experiments. So if we don't know anything, we need to start from somewhere. Bayesian optimization cannot tell you anything if you don't know anything yet about what to start from. So we just start with 3 completely random guesses. So we pick 3 values of x. It's like roughly 1, 1.8, 2 point something, 2.9. And we just run these experiments to see what is the outcome. So we observe 3 different values of f. And now if we kind of ignore the black line, it looks like this first one is the best. So if you're now a human and you look at these points, what would you choose next as the next experiment to do? Sorry? Yeah, you would go near to 0.1. So keep that in mind. This near to a certain point in parameter space will play a very important role later. So our intuition is to go near something that is already good in our observations. If we look at the gradients, someone suggested gradients later, we could now also look at the gradient here. So we could vary this point a bit, we could vary this point a bit, we could vary this point a bit. Then we could already see that like going near this here means we have to go in between because the gradient is here going up a bit. So gradients could help, but they're not necessarily very data efficient because even this scenario, you already need 1 or 2 additional experiments to get the gradient. If you have higher dimensions, you need more experiments to measure your gradient. So this is not necessarily very data efficient. So today in this lecture, we will completely ignore gradients. We will not base our decision making on any measurement of gradients. We will just look at the observations, but not at all try to find what direction is better. Okay, so we have initial data points, and now what we do is we fit a machine learning model. Of course, this is very simple. It's only 3 data points, so we need a model that doesn't overfit too much. And what we need is a machine learning model that doesn't only make predictions, but that also tells us something about the uncertainty of the predictions. So we can fit our initial model, and this is now, as I mentioned earlier, a Gaussian process model. But you can in principle use any other machine learning model that does predictions and also uncertainty estimations. And you might want to use something that does not easily overfit. So if you now use a Bayesian neural network to train on these 3 data points, then it's very likely that it will do very crazy stuff outside of these 3 data points. So it will fit them perfectly, but it's completely unknown what it will do outside. Whereas the Gaussian processes are kind of easy, like they're stronger regularized, so they don't do crazy stuff outside. So they don't overfit easily, and we get like something like that. So a curve that looks like that blue curve here, and an uncertainty bound that looks like the blue area. And you see that the normal vanilla version of Gaussian processes here perfectly fits all these points. But this can also be extended. So if you have measurements and you already know that there's a certain uncertainty connected to your measurements, you can also use a Gaussian process model that takes that into account. So you're not forcing it to perfectly fit the data points, but you can make a Gaussian process model that's not having 0 uncertainty in these data points. So you also have some leftover uncertainty that you can tell the model in these data points. And now what we do is we look at this blue model, because that's all we know. Of course, we don't know the black curve. I mean, we know it now, but in reality, we don't know it. So we only look at the blue curve now and the uncertainty and think about what would be the best next point to go.
Highest uncertainty?
Sorry?
Highest uncertainty?
Yes, we could look at just where's the uncertainty the highest, so where's this blue band largest, and that would tell us go here, either very left to x equals 0, or go to the very right to x equals 5. That would be very good data points to look at, because we already know from looking at that Bayesian optimization, at that Gaussian process model, that we kind of don't know anything about these points. So there could be new maxima, there could also be not new maxima. That is the exploring strategy. So we want to explore everything that's unknown. There's also the opposite. What else could we do? Between the points means?
Between those two.
No, sorry.
The two initials that I have, because it looks like I have a lot of uncertainty there.
Like in between here. Yes. How can we formalize this? Yeah. No, but behind you.
I also want to say it's a different suggestion. Like you could also go to the point where you expect the highest potential of improvement.
Yes. You already know about Bayesian optimization, so you can look at this upper line here. That's basically the blue line. That's the average prediction plus the uncertainty, and that's like kind of the potential of what you can do if you're lucky. So the Gaussian process model tells you very likely the new observations will lie on that blue line, but there's some probability that they would lie 1 standard deviation above. So let's assume this is the 1 standard deviation line. Then with some 30% chance, you could be on this upper line here. Of course, you can also be unlucky and be on the lower line, or you can be very unlucky and be even lower. But there's some certainty, some probability that you would lie on this upper line or even above. So what you could do is you can use that upper line or the maximum of this upper line to choose your next experiment there. And you already see there's a lot of choices here now. And this is called in Bayesian optimization the acquisition function. So we need to define a function that measures the informativeness of our next experiment. And if you're an explorer like him, you only look at the uncertainty. You say your acquisition function is just the uncertainty itself. And this is very useful if you want to explore the whole space, if you really want to understand the relationship between f and x and minimize your uncertainty, then this is a very good acquisition function, because it helps you pick the data points that minimizes these uncertainties, that cover as much area as possible in order to have a good understanding of nature, that black line here, in the whole parameter space. If you want to be very efficient, then you do it like her. You measure the upper confidence bound or some other thing that mixes the mean prediction and the uncertainty. And if you're really, really impatient and you want to make good results as quickly as possible, then you only look at that blue line and take the maximum of that, because that's the most likely outcome of the experiment. And then you just go to the maximum, which would be maybe here, and then measure your next experiment there. That's the opposite of exploring, that's exploiting. You're exploiting what you have seen so far, and then just fitting the best fitting line and going to the maximum of that. This is if you have a very, very small experimental budget. I don't know, you can do 2 or 3 more experiments, then this would be a good strategy. If you have a medium-sized budget, you can do many more experiments or some more experiments. You should go to an acquisition function that balances the explorative character of looking at the uncertainty and the exploitative character of looking at the maximum of your blue line. So we can now define this acquisition function. In my slides here, I use the upper confidence bound, so the upper bound of this blue area here. And this is now visualized here. So this is just exactly the same line. And we're just looking at all possible values of x and picking then the maximum of this. So we decide our next experiment will be at x equals to 0.3. And this is then the next experiment we do. So we go to the lab, put our knobs to 0.3 and see what comes out. So we're measuring the black function here. That's our nature, the unknown function. And we see that the next data point is quite low. So we're quite unlucky here. It's even lower than the lower confidence bound here. So we went to a point that didn't give us a very good result in terms of we didn't come closer to our objective. But at the same time, it will minimize this uncertainty here quite a lot. So if we now fit a model to not only 3 data points, but to the 4th data point as well, then this model will look very different. So it will basically reduce the uncertainty in this region quite a lot. So we know now that this region, by just doing one additional experiment, is kind of excluded from being interested at all. So we will probably not ever go in this region of x equals to 0 to 0.5 again anymore, because we know that the value that we observed is low, and because we already have the second value here, we know that very likely it will not change a lot. So the uncertainty is also very low. So with no strategy, neither the explorative strategy nor the exploitation strategy, we will go very close to this region again. So we excluded with just one measurement a very large parameter space, and that makes us data efficient. So now we can again look at the upper confidence bound. So let's update this function here. Then we get this as the upper confidence bound. Again, we look at all possible parameters. We find x2 equals to 3.7. This would be a good next experiment to do. And then we go to the lab. We measure this value here, and now we are quite lucky. Now we found an experiment that's even above the upper confidence bound. So this is like a less than, 20% chance of finding this. But we still found something that's very close to the global optimum here already. So we can then again update our Gaussian process model. Now the Gaussian process model also reduces the uncertainty here quite a lot, but there's still some uncertainty in this direction, and it even thinks that it might go further up in that direction. So if we now look again at the upper confidence bound of this, we find this shape here, and there's another expected optimum in this acquisition function a bit further to the right, 4.1, 4.2. So it tells us go to 4.2 next. Again, we measure it, and then we're a bit disappointed again that it doesn't even further increase in that direction. But at the same time, again, it updates our knowledge about this region of parameter space quite a lot. So the uncertainty shrinks. There's still some leftover uncertainty here, but it's not very likely that we will find another optimum here according to the fitted model. You're already shaking your head. No, but you're just, a bit skeptical. We can talk about it in a second. So we basically already fit nature, the black function, quite well. So the blue line and the black line agree with just having apart from the 3 initial experiments, 3 more experiments. So we went from a very weird, not identical model to a model that almost perfectly fits nature with just very few additional data points. And this works very similarly in higher dimensions. Of course, you will need a few more experiments, but you can also do that in higher dimensions and explore parameters x1, x2, x3 at the same time and find optimal settings of your x1, x2, x3 knobs in order to find the most informative data points. You have a question?
Pascal, what's the difference between Bayesian and other algorithms for optimization like PSO and genetic?
I will.
That's very easy with data efficiency.
Yes, exactly. I will get back later to your question. But yes, I mean, the short answer is our objective here is data efficiency. And there, I would say, like, Bayesian optimization is the sweet spot for if you have very high dimension parameter spaces and you can run many experiments in parallel or many simulations or many whatever, then maybe also time efficiency will play a role. You don't want to iterate for the next 2 years. You rather want to parallelize, and then a mixture probably of Bayesian optimization and genetic algorithms or particle swarm might be the most optimal solution. I would say right now I don't see a lot of scenarios where pure genetic algorithms would be super applicable unless you can go to millions of data points. If you can do that, then you cannot fit easily your machine learning models anymore. There's an overhead of fitting the models, and then just purely exploring using particle swarm optimization or genetic algorithm variants might be more efficient. But in most actual real-world scenarios, I would always try to see whether we can learn something from the incoming data points and then have a mixture of active learning and some strategies like genetic algorithms to explore. But it's very like problem specific then, like what's the budget that you have, how many data points can you generate, what's the dimensionality of your space, and then you can determine what's the most efficient algorithm.
Well, it's maybe just a problem of the experimentalists, but some of us are computationists, so we can produce a lot of data. So if we just move a little bit just further, and we can produce maybe thousands or at some cases millions of
Yes.
data.
Then some active learning strategy could be good. And if you have very large parameter space, you need to determine what could be good points to explore. And then you use a genetic algorithm or particle swarm to evaluate what are the most, like what are possible points. Then you use active learning to pick the points that are efficient, and then you can iterate. So that would be a nice hybrid approach. But doing just brute force particle swarm, I think it's also not very efficient, as long as you can train a model.
Another question. These days, everyone talks about reinforcement learning. Do you
That's
think
the-
it's applicable for computational chemistry or for experiments?
I'm very skeptical with that because reinforcement learning is not really an optimization algorithm. So if you have a optimization problem, then you should use optimization algorithms or search algorithms, like genetic algorithms. But reinforcement learning is usually, the setting is you have an environment that's uncertain. So you have something that, in the worst case, plays against you. So you can't say there's an optimal point in this space, but you're learning strategies of play with this space. And that typically is not the setting we have in material science. There might be cases where you can phrase your problem as like a adversarial problem where you need to find a strategy rather than a optimal point. But as long as you really have a setting where you want to find an optimal point, then reinforcement learning, in my opinion, is not typically the best way to go. At the same time, the data efficiency of like modern reinforcement learning algorithms is the worst you can imagine. Like if you look at how many data points or how many episodes people use to train the best reinforcement learning algorithms now, we are talking about billions, not millions of data points, but billions. And then even our simulations get too costly. Even if it's just like a semi-empirical, quick homolumo gap calculation, you don't want to run billions of them. But in reinforcement learning, you typically run really for multiple weeks on very efficiently implemented games or whatever you want to do. Billions of episodes to train your agents, and that's tricky. So I don't see in many scenarios that reinforcement learning should be used, but if there might be some use cases, it really depends on your application. Was there another question? Yes?
How can you make sure that that once you are kind of complete with the optimization, because in this case now the upper confidence bound would always point you to the maximum.
Yes. So if you now repeat, you will always
Yeah.
be very close to that.
How can you make sure that your model is so if it's a more the parameter space is larger, I guess it's harder to get to this point.
Yes.
Confidence bound. But is there a way to make sure that kind of the optimization is complete and that your model is describing the problem well enough?
I'm not sure if there's any mathematical guarantee that you can find a global optimum in a certain number of points. You need to then, if you want guarantees, you need to have certain characteristics of the function you're fitting. So if you know something about that function, and for example, what's the steepest gradient that you can expect and things like that, then there might be ways of guaranteeing certain efficiencies. If you don't make these assumptions because you expect there could be a noise in your function, so you don't have perfect measurements, or there could be even steps, which would be much worse, or very, very steep inclines, then all the mathematical guarantees are gone. So you might just miss global optima. So if you imagine there could be a function that looks very smooth like that, but then in one area it just has a peak. There's no guarantee that any algorithm will find that peak apart from a brute force search with a very fine grid, because you don't know anything about the function. But if you know things about the function, about the smoothness of the function, I think there are some guarantees that you will find basically the global optimum, because you then can look at the steepness of your fitted model, and that steepness, if that's not too much below the steepness that you expect, and you can assume that there's nothing surprising in between data points anymore, and then you can kind of know that you converged. But very often in experiment we don't know these assumptions. We don't know if there's phase changes that lead to a jump in your function, or noise that might, I don't know, if that point is very noisy, then maybe you're informing the Bayesian optimization about the wrong value. So very often if you have noise, you should also try to quantify the noise in these data points in order to tell your optimization algorithm how noisy your observation is. And then it might also revisit one of these points later again to see whether there's actually some potential there. So if you have noisy experiments, also consider them here. Yes?
Yeah, like you mentioned, if you have some steepness or sharpness, like if there's a phase transition,
Yes.
something like that, are there any algorithm schemes that are more well suited for data that is not so smooth, or can you only compensate by more data points, finer grids, but basically the same algorithm scheme?
I mean, in principle, if you know how steep you expect changes to be here, you can also use that as prior knowledge in your Bayesian in the Gaussian process model. So the Gaussian process model has a hyperparameter that is automatically determined in the normal scenario that is trying to fit how quickly can things change here. In 20 minutes you will understand it better. So there's a hyperparameter that tells you, or that tells the model how steep can the changes be here. If you don't know that in advance, it will be optimized. So it will kind of look at the observations, look at how quickly do they vary, and then it will just set the hyperparameter to whatever it expects. But you can also force it to be smaller. So if you have these 3 initial experiments, and they look quite smooth, but if you know that there might be sudden changes in it, then you can fix this hyperparameter, and then the possible functions that your Gaussian process model can fit, and also your uncertainty bounds, will be not small here, but they might be very large here. So it might explore also things in between. If you know that, and then you can set it, and then you can let it explore more, but that also makes it more data costly, because then even though you know points here, you don't know what's going on in between, so it will explore more points also in between. the big problem, and that's also work that is being in development, is if you have a changing smoothness in your space, because that's the optimal thing. If you know there can be varying smoothness, but it's only in a certain part of the parameter space, so you expect, I don't know, a phase transition in that region, but not in this region, then you want to have a smoothness that depends on X. And that is right now in the Gaussian process models still a bit tricky to do. There's like some papers, some approaches to do that, but it's very tricky to like have let's say automated library that just does everything for you. You just tell it here and here I expect transitions. But then you can have a very data efficient way of making assumptions that it might not be smooth here, but more smooth here, so it doesn't explore as much here as it does here. And then you can be data efficient again, but you need a lot of assumptions and quite complex extensions potentially.
What's the name of it again? Hyper something? Hyper.
I need to look it up. I don't know it by I mean, there might be different names. All right.
Just a question. What happens if you have one or more parameters? This is the case for one parameter that control the results of your experiment. If you have more than one parameter that control your experiment, what happens?
It just explores combinations of them. So
yeah, but I mean, sometimes it can happen that the parameters that give a result of the experiment are also not in the same direction, all right? You can maximize in one direction and you can minimize in another direction, so it became more complex. So the complexity.
I mean, the algorithm just doesn't change at all, no matter how many parameters or dimensions you have. Yes. I mean, you just fit a Gaussian process model that fits f as a function of x1 and x2. And then you look at the acquisition function of that, and it tells you this combination of x1 and x2 is the most informative next data point. I just can't easily visualize that here. I mean, 2D you could still do. 3D would be very complex to visualize. Yeah, you have many, yeah. That's what I mentioned at the beginning. Yeah.
Like room temperature, pressure.
Yes. But that's, yeah. Yes, absolutely. So this is just for visualization purposes. Everything I will show you later in implementation is for multiple parameters. There was one more question, or?
I was wondering how this model is depending on the quality of the uncertainty estimation. Because if you have some point in which you overestimate or underestimate the uncertainty, it could change all the landscape that you're.
That goes in a similar direction to what I just explained. You can have uncertainty, and you can inform the Gaussian process model about the uncertainty of your measurements, but it assumes that your uncertainty is homogeneous in space of X. So the uncertainty is always the same. If you want to have models that have an uncertainty that depends on X again, that is more tricky. So there's extensions that work very easily if you have a global uncertainty and you just assume it's more or less the same everywhere. But if you know that in this case, in like small values of X, you have higher uncertainty than in higher values of X, that's very tricky to model. There's ways of modeling this, but they are not just out-of-the-box models. So if you really need to model that, you might want to talk to someone who is developing Gaussian process models and knows about the more or less like last 2-year, 3-year developments in that area. Yes.
Change. So it's the real world.
Yes, that's why people are working on that. I think. I mean, Gaussian process is like still a very actively developed area. Also to scale it to larger data point sizes. I mean, we will talk about the efficiency of fitting the models later. There's a lot of development still in that area, but it's still a tricky problem to model because it adds a lot of complexity if you have varying uncertainty and so on. And just even if you assume fixed uncertainty, it will already help your exploration algorithm. And you will certainly be better than grid search or random exploration. So even if you don't model everything perfectly, it will give you an advantage. It might not be perfect, but it will give you an advantage nonetheless. Okay. No more questions? Then I will continue. So, I mean, as it was already mentioned, if we now repeat, we will always go to the same point again and again. So there will almost be no update anymore. So this is kind of converged. And you can have some convergence criterion. If you do the same decision 3 times in a row, you just stop. Or if your model doesn't change anymore, you can just stop it. So you, at some point, stop this iterative algorithm. So now, as I said, the core is having a model that has not only predictions, so not only a blue line that fits the curve, but also uncertainty estimation. So I will now take a couple of minutes to introduce the Gaussian process model. This will be a bit more mathematical. You might benefit from it. Maybe you don't care about it, but let's quickly go through it. So to explain how a Gaussian process model works, we still need to quickly talk about Gaussian distributions. So we can have, and now we have here two variables, f1 and f2, and those can have certain distributions. So we have different observations of f1 and f2, of combinations of those, and those could, for example, look like that, or they could be correlated like that, and we can model these distributions very often as Gaussian distributions. And a Gaussian distribution has a couple of parameters to quantify or to describe that distribution. So it has mean parameters, mu1 and mu2, and it has these sigma parameters, which are the covariance parameters. And the mean parameters are telling us what is the mean of the observation in f1 direction and f2 direction. So if we now look at all of these blue data points, and we think about what is the mean f1 value of all of them, we see that this is very close to 0. So there are some negative values, some positive values, but the mean is more or less 0. The same here, if we look at all of these points here, and their f1 values, we also see that the mean is more or less 0. Same for f2. If we now look at all the points, but look at their y coordinate here, we also see f2 is more or less on average 0. Same here. So these two distributions, even though they look very, very differently, they have the same mu1 and mu2 parameters, which are both more or less 0. The difference in these two distributions is the covariance. So these f1 and f2 observations are completely decoupled. For any given value of f1, you can have basically also any given value of f2. Whereas here, if you know the f1 value, then you already narrow down f2 quite a lot. So they are highly correlated, and knowing one tells you a lot about the other. And that is telling us about, that is described using these 4 parameters here. The ones that are on the diagonals here are telling us what's the width of the distribution. And again, the distribution of f1 has a certain width. f1 here has a certain width, and they seem quite similar. So both of these distributions will have a very similar sigma 1,1 value, because the distribution width is similar. Same for sigma 2,2. The width in this direction is very similar to the width in this direction. But the difference between these two distributions are the off-diagonal elements. And those are basically quantified by the expectation value of having at the same time an f1 value that's bigger than its mean and an f2 value that's bigger as its mean. So if the points are correlated, that means if f1 is higher than the mean, the 0, then it's likely that f2 is also higher than its mean. That means this sigma 1, 2 value would be positive. If we know that f1 is higher than its mean, then f2 is lower, so the opposite correlation, then this value would be negative. And if we don't know anything about f2, when we see that f1 is larger than the mean, then this is 0. So basically, if we now look at the solution, this distribution here can be characterized by having means in both variables, having a certain standard deviation in both variables, and having no covariance or correlation between the two variables. And this distribution here has some degree of correlation. So if we know the value of f1, we know something about f2. There's still a bit of noise, so it's not a perfect line. So this is not 1 on the off-diagonal, but it's close to 1. And this is a very, very useful way of modeling data. So if you have observations in a high-dimensional space, so think about again the experiment that I showed earlier. So we have some catalyst experiment. We measure the catalytic efficiency at multiple different data points. And now we can model, for example, the catalytic activity at room temperature on the F1 scale and at a higher temperature, let's say at 50 degrees on the F2 scale. And if we know that at room temperature and at elevated temperature, there's no correlation between the observations, then this could be modeled using a distribution like that. But if we know that we have some efficiency at room temperature, we will also have some efficiency at higher temperature, then this can be modeled like a correlated distribution. And this is exactly the idea that we do here with Gaussian processes. And there's one very, very nice property of Gaussian distributions. We can model those as continuous distribution functions. So basically this model of our function can be expressed as a probability density here. So we can say we have observations. We determine these parameters, mu and sigma. And then we can model it as this continuous probability density. So we have here F1 and F2 values. And for every combination of F1 and F2, we have some probability to observe a data point. So if we look from top on this distribution, it would look roughly this diagonal shape here. So the maximum is at 0, 0. And then there will be some density at positive values of F1 and positive values of F2. So there will be a maximum in the left corner and a maximum in the front corner, and it's a bit more narrow in these two other directions. So we can model this as a continuous distribution. And now there's a very, very cool property. If we cut this distribution here, so if we cut it at a certain value, for example, F2 equals to 3, and we look at what is the distribution then in F1, we get another Gaussian distribution. So all the cuts of high-dimensional Gaussian distributions are again Gaussian distributions. And there's an equation, I will not derive that equation today, that tells us if we cut it at a certain value of F2, what is the remaining distribution of F1 given the joint probability distribution. So if I know the joint, all these parameters of the joint probability distribution, so I know the means and the sigmas, then I can easily calculate what is that red line here. So what is the probability distribution of that red line? What is its mean? And what is its standard deviation given these values here and the observations that we had? So given the value of F2, so 3.2, where we cut it, and all the other parameters that we know from the joint distribution, we can calculate the marginal distribution, basically, or the conditional distribution. So we know what is the most likely observation of mu1 given mu2. And that's exactly in this two-dimensional scenario here. We can learn the distribution very easily of what is F2 given a certain value of F1. And that's very useful to do that mathematically. So if we have an observation of F1, the reactivity at room temperature, we can then learn how do the room temperature reactivity and the elevated temperature reactivity correlate. And then if we have a certain observation at room temperature, we can measure or we can predict what is the remaining probability at a higher temperature. And that is the idea behind Gaussian processes. We model our observations as these multi-dimensional, multivariate Gaussian distributions. And then the actual observations are cuts. And I can do predictions for the unknown possible experiments that I can do. So let's go further here. We can say in the beginning of our experiment, we have multiple possible observations of X. So X is our knob setting again. Activity at room temperature at 40 degrees Celsius, at 80 degrees Celsius, and so on. And if we don't know anything, then we have to assume that the reactivity Y as a function of these X values can be anything. So we have Gaussian distributions of possible observations, but we don't know anything. So we just set there's some certain mean value, we can set it to 0, and a certain standard deviation of activity that we can set to a certain number. So we, in the beginning, don't know anything. But we know, and that is something that we explore in our daily life, that more similar settings of our knobs will relate to more similar observations. I think that's something we can all agree with. You already said in the very beginning of this lecture, we go close to very near to very good observation we had in the past. So we make always the assumptions that things are not completely randomly fluctuating, but things are to some extent smooth. So we assume that once you have an observation at x2, for example, this will tell you more about x1 than it will tell you about x3. Just because x2 is more close to x1 than it is to x3. So we can guess the off-diagonal elements here. We don't know anything about the expected means. We don't know anything about the expected standard deviations. But we already, even though we didn't do any experiment yet, we know something about their correlation. We know that x1 and x2, so this off-diagonal element here, is higher because they're more close to each other than the correlation between x2 and x3. That would be that value here. And it's even higher than the correlation between x1 and x3. That's this very off-diagonal element. Just because we know they're further apart. So it's not as valuable to know x3 if you want to measure x1 or if you want to make some assumptions. And that can be mathematically defined. So you can just assume a function that tells you about the correlatedness of two data points. And a very interesting or nice choice of this function, and this is now called kernel, that's the similarity between two observations, could be this Gaussian kernel that basically says if 2 points, x1 and x2, have a certain difference, we just say that their correlation is the exponential function of minus that distance squared. That has very nice properties. So if we go to infinite distances, we have an infinite distance between x1 and x3, then this function will go to 0. So those experiments are just completely uncorrelated, and knowing what comes out at x3 does not tell you anything about x1 if they're infinitely far apart. If x1 and x3 are identical or very close, then the distance goes to 0, and e to the minus 0 is 1. So that tells you if points are very, very close to each other, then their correlation will be very, very high. So if I measure two almost identical experiments and I expect two almost identical outcomes, otherwise there might be jumps, and that is not covered here. That's why jumps, meaning very, very similar values but very different outcomes, cannot be modeled easily or at all by Gaussian processes here. So even though we didn't do any experiment yet, we know how correlated certain outcomes should be. And we can model that using this exponential or squared exponential kernel. And now we can do measurements. We can say we measure x1, x2, and x3. We measure 3 values of our functions. And now we can ask, what is the most likely outcome of a measurement here at x, somewhere between x2 and x3? So what we can do is we can model all of these 4 possible experiments as 4 dimensions in our multivariate Gaussian distribution. And then we cut this multivariate Gaussian distribution at x1 equals to f1, x2, f2, x3, f3. And we cut it, and then we get a remaining distribution that tells us what is the distribution, the most likely outcome at any given data point. So we learn something about any value of x star. So we can do that. We can say our 4 observations at x1, x2, x3, and x star can be modeled using this multivariate Gaussian distribution. We again assume there's no means known at all. We already know the correlation matrix because we use the square exponential kernel. So we model it as this distribution. And then we cut this distribution at the observed values. I mean, I can't visualize that because I can't visualize 4D distributions. But you're kind of cutting it at the observed distributions. And then you're asking what is the probability density of observing a given functional value f star at the position x star given all your previous observations. And you use?
I'm terribly sorry. Do you mind re-explaining how we arrived at the x star? And hopefully
well, we didn't do that yet. I mean, I didn't explain it yet. I just said this is something that looks kind of, I mean, we basically model it in a mathematical way. So we can model all our joint probability distribution as this Gaussian probability distribution. And then we do that trick that I mentioned earlier, and we use the same equations that I mentioned earlier. Where was it? So we can have a joint probability distribution now in 4 dimensions. So we have f1, f2, f3, and f4. And then we cut it at the observations of f1 equals to whatever we observed of f1, f2 as the observation of f2, and so on. And then we ask what is the remaining probability distribution of f star given all the other observations. And that's, as I said, is defined by knowing these values here. That's this 4-dimensional 4x4 matrix. And the observations that we already had. And that goes into these equations. So if you look at these two equations, that's the mean and the standard deviation of the F1 distribution given these parameters. So we have mu1, we have mu2, we have the sigma 1, 2, 2, 2, 2, 1, and 2, 2. So they all go in there. And the observation F2. So we know F2 has a value of -3. That's the observation. And with these numbers that we all know, we can model, or we can say what is the probability distribution of F2. And now we just extend this to 4 dimensions. So we model 4 observations, 3 that we already did, and 1 that we want to learn something about, as here a 4x4 grid. And we just make assumptions about how correlated these data points are, because we know how far away are they. And then we can do this trick by cutting it. And we say the new mean observation of X star has a certain value, and that depends only on this kernel matrix here and the observation F that contains F1, F2, F3. Those are the experiments we already did. So we know everything that we need to know to predict what is the most likely mean and also what's the standard deviation of a possible observation at this point here. And this basically...
So the F is like a sum of F1, F2, F3? Or
Yeah, exactly. F is a vector that contains F1, F2, F3. That's the previous observations, our experiments that we did. And the K, that K star is that, let me see, K star is this part of that 4x4 matrix. So we split this 4x4 matrix into different blocks. There's the correlation between the previously done experiments, that's the matrix K, and we need to invert this. And this is also the costly part of the Gaussian process model. That's kind of the training, is we look at all the previous observations and their correlations, and then we have to invert this matrix, and that's quite costly if you have many observations. And then we have these off-diagonal blocks here. That's the correlation between the previous experiments and the new experiment that we want to do. That is K star. That goes in here. And then we have this correlation, or like the expected width of the new experiment. That's K star star. And that also goes in here. But typically you don't know anything about it, so you just set it to random number. So you can basically, you know everything in these equations in order to make a prediction of what is the most likely distribution of a new data point. And now you don't only do that trick for one particular data point, but you do it for all possible data points, and then you get something like that. In every data point, you get a new distribution with a given mean and a given standard deviation. And by having these assumptions that similar data points will lead to similar outcomes, you automatically get this narrowing. So once you approach a previous experiment, the standard deviation will go to 0. So if we look at this equation here, there will be basically a certain amount of zeros in this kernel matrix here. So this overall equation will go to 0. So we will basically fit the data points perfectly. If we go away, the standard deviation will be higher. And we will, at the same time, using the equation for the mean, get a very nice, smooth fit through all the data points. And the hyperparameters that I mentioned earlier about the smoothness is basically a parameter that I omitted here. You can, in principle, introduce a parameter here. So it's e to the minus alpha times the distance squared. And if that alpha is a very small value, that would mean that even if you have very large distances, you still assume that the experiments are highly correlated. And that means you assume a very, very smooth observation. If you make a very large alpha parameter here, that means that this value of the kernel goes very quickly to 0. So you go away a bit from some experiment, and you already know nothing about the neighboring data point anymore. And that would model a very strongly varying function. And typically this alpha parameter is kind of behind the scenes optimized and trained or fitted to your data. But if you know about the varying or the smoothness of your function, you can also fix a alpha parameter that kind of tells you how much do I know about x2 if I know x1, depending on how far away they are. So you can fit that, or you can fix that parameter as you want, and then you can model certain variations of functions.
If I may, so on the maximum of the current rate?
No, that we don't know yet. We just try it for all. And that's kind of fitting the Gaussian process model, is trying it for all possible data points that we could in principle measure. We kind of do that mathematical trick of getting the mean and the uncertainty of that particular point given the other points that we have. And then this is basically the Gaussian process model, what you see here in red. And now you can define the acquisition function after fitting that model and defining what is informative. Do I want to go to the highest standard deviation? Then I would measure here, because there's the standard deviation is highest. Or do I want to go to the highest expected value? Then I would probably go here. So you're first fitting the model, then you have your Gaussian process model that tells you a mean and a standard deviation, and then you define your acquisition function and select the next point to do. But hypothetically, you kind of do it for all possible points and then select afterwards what is the most informative point.
Thank you.
Okay, I'm just looking at the time. This was one way of motivating how Gaussian process model works, using that cutting of multivariate Gaussian distributions and getting the conditional distribution. And I said I didn't derive these equations, I just assumed that we can derive them. And this is what we will implement in the afternoon. So you can, in principle, implement it yourself very easily. We will implement these two equations and then see how we can fit the Gaussian process model to some data points. There's another explanation. And if you want to learn more about this, there's a very nice book that explains both of these ways to intuitively understanding Gaussian process models. I will have the reference later in my slide. And the other explanation, in my opinion, is less intuitive than this one. So I explained this one first. The other one, I will go very quickly because we don't have that much time anymore. The other one is saying a Gaussian process model is basically a distribution of functions that can be fitted through these three data points. So a Gaussian process model is fitting all possible functions, or with certain conditions, that can fit these three data points at the same time. And there's a trick to do that. So if we now have these three data points again, and we use these functions here, we can now sample possible points at a given value of x star. That's what I already explained. So we can plug in all the things we know about observations and the correlations into these equations and get a mean and a standard deviation for x star observations. And then we can sample from these. So if we have the mean and the standard deviation, we can sample one point, we can sample many points at x star, and we get a distribution here. And there's a mathematical trick that allows us also to sample entire functions that fit these 3 points. So we don't sample independently values at different values of x, but we sample entire functions. And I will not go into details, but you can in principle use that kernel matrix here and do something that's like a square root of a matrix. That's this Cholesky decomposition. So you get this L matrix here, and you assume that the sigma is basically the square root, or the square of this L matrix. And with that, you can do a trick where you sample entire functions. So you sample basically vectors for many, many different values of x star simultaneously that all kind of have these properties that they vary in a certain way according to your assumptions about how quickly can the function vary. How quickly do you assume that the values change if you go away from your observations? So you can sample entire functions, and you can do that many, many times. So a Gaussian process model is not fitting one function, but many, many functions. And then it looks at the standard deviation of these functions. And these standard deviations will give you, again, a uncertainty bound, and the mean of all these functions will give you a certain mean prediction. So the alternative way of explaining Gaussian processes is we don't fit one function to our observations, but an infinite amount of functions that all have given conditions about how strongly they can vary. And this strength of variation is all defined by our kernel choice. So we define how quickly do we assume that the observations can change if we move away from previous observations. And this will tell you what type of functions you can fit. And then we can fit basically a lot of functions. And the property that all of these functions obey is that at any given cut of these functions, you get, again, a Gaussian distribution. So no matter where you cut all of these functions, if you record the values, you get a Gaussian distribution. This doesn't look really like a Gaussian, but if I fit more functions, it looks more and more like a Gaussian distribution. So the more I sample, the more Gaussian this will look like. So in any given point, I will give a Gaussian distribution that's defined by a mean and a standard deviation, and that can be then used for the acquisition function. So in the end, we have a mean of all these millions of functions. We have a standard deviations of all these millions of functions, and this is our final Gaussian process model. So this is an alternative way of saying what Gaussian processes are doing. They're fitting infinite many functions with certain side conditions to obtain this mean and standard deviation. The alternative way is it kind of models your data as a multivariate Gaussian distribution and then makes these cuts in order to get the conditional distribution at any given point. The result is the same. It's the set of these two functions, and that's what you basically have to implement if you want to fit your Gaussian process model. I'll skip that slide. So now let's go back to Bayesian optimization. We now know we have a model, Gaussian processes, that can not only predict a mean for a new data point, but also an uncertainty. So it's a model that intrinsically has uncertainty estimation, and we can now go back. We have now a model that makes predictions and uncertainty estimation, and we now want to define an acquisition function. And I will only have two, 3 slides about this. What time is it? Yeah. We need to somehow mathematically also define what is the informativeness of a next data point. And we already said it could be the upper confidence bound, and this is the most simple one. So we just say the acquisition function u of x is the mean prediction, that's the blue line, plus beta, some factor, times the uncertainty. We can set beta to 1, and then we would get the 1 standard deviation uncertainty bound. We can also set beta to higher values. That would be more explorative. So we go to points where the uncertainty is higher. We can also set beta to small values, in the extreme case to 0, and that would be the more exploitative character. We only go where the mean prediction is high. We don't care so much about the uncertainty. There's other ways of doing that. For example, the expected improvement acquisition function, and that is basically we look at the previously best observation that we had. So we look at these 3 data points. The highest one was this, that's f star. And then we look at the difference between our function and the best observation so far, and then calculate the expectation value of that. So what is the expectation of having a higher observation, for example, in this region here? And there's some certain, like some probability that we can observe something higher than the best one we ever observed. So the expected improvement acquisition function has like a maximum here, because there's some probability that we can get higher. It has almost nothing here, because you see that the points are going lower than the best one we observed so far, and there's not much probability that there's something better. So it's almost 0 here, but then there's again some probability that this observation will be higher than the best one so far. So we again have a maximum here. You already see, if we now compare expected improvement to upper confidence bound, they look on the first glance very, very different, but the maxima are very similar. So there's a global maximum here, a local maximum here. That's the same one for this one. So the next experiment to choose would be very similar, independent here of which of the acquisition functions we use. You can come up with your own acquisition functions if you know more about what exactly you want to achieve. And you will see that there's many acquisition functions implemented in the typical libraries that do that. And it's a bit of a assumption that you have to do what acquisition function to choose. The same as you have to assume what kernel you want to assume for your Gaussian process model. So there's also certain choices you have to do when you do Bayesian optimization, but those are not very, very sensitive typically. So if you use a standard kernel and expected improvement, then typically this should work quite well. So you don't need to vary a lot all the hyperparameters that you have. Okay. I think due to the time, I will stop at this point and take a couple of questions before we go to the break. So are we